We are in section 4.4. Section 4.4, we're going to talk about contingency tables. And in this section, we are interested in finding joint and marginal probabilities from these tables. Okay, so first of all, what is a contingency table? A contingency table is also called a cross-classification table. It's a table that shows the distribution of scores for bivariate data. That is the frequency distribution of bivariate, meaning there should be two variables in your data. Okay. Now, before we actually look at an example, let me give you a general structure of what a contingency table may look like. So here I have a table. Now this table is made up of rows, so I'm going to call this row 1, row 2, and just suppose there's only 3 rows. The rows can go on for longer than that. And then my columns, I'm going to have column 1, column 2, and column 3. Okay, so the variable that forms the rows is called a row variable. And row 1, 2, 3 are levels for that variable. And of course, there's the column variable. Okay, and column 1, 2, 3 becomes, those are the levels of the column variable. Now, if I actually form a table here that's made up of rows and columns, and there you have it. So I have our contingency table here. Now, in this contingency table, every contingency table, in fact, any row-column combination forms a cell. So this is a cell in that table. And here's another cell. In fact, there is 3 by 3. There are 9 cells in this contingency table. Okay. Now, for this contingency table, any row-column combination that is a cell, it's called the joint event for row column 1. Okay, so row-column combination. So for example, what I'm shading right now, this would be a cell. So this would be a joint event. So any row-column combination forms what we call a joint event. And there you go. That is a joint event that row 2, column 2 levels of each of those variables occur. And there's going to be a frequency sitting there in these tables. You'll see an example in a moment. Okay. Now, these rows themselves, row 1, 2, 3, that lie on the margin, and the columns, they form the margin of the table. Margin. So I have a margin here and I have a margin here. Okay. Therefore, we have, again, a contingency table is made up of rows and columns. The intersection of any row column creates a joint event. And each of the rows or each of the columns on their own form the margin of the table. Okay. Now we are usually interested in defining these events in terms of marginal probabilities or joint probabilities. So the margin turns into a marginal, joint events turn into joint probabilities in a moment. So here's an example that I have. Okay, this actually was from last semester in one of my classes. And I asked the students, if anybody had tattoo or not. Very simple question, yes, no kind of question. And I divided these students into the responses, that is, not in the class physically, but the responses, I divided it into 2 groups, gender, male, female. So I would like to establish some probabilities here. So first I've defined these events. H is the event that the student has a tattoo. N, event that the student does not have a tattoo. And M is for male and F is for female students. Okay. Now, let's say I'm going to choose a student at random, and I want to find these probabilities now. Okay, I want to find probability the student is male or female, has a tattoo, or this instead of D, sorry, that should be N. I mentioned N and I put D there by a coincidence. Okay, so these are again marginal probabilities because these belong to the margin of the table. And then the joint probabilities are row-column combination. So there are two rows, meaning there are two levels for the variable tattoo, and there are two columns that would correspond to the two levels of variable gender. Now the joint probabilities I have in this table, there are 4 joint probabilities. I only used 3 of them. We're going to look at 3 of those. Okay. Now, if I form the totals, by the way, if I form the totals here on the margins of the table, these totals become for the first row, there's 20 students that had tattoo in that class. That means 30 did not. There were 20 male and 30 females. This pure, again, coincidence how the numbers turned out here. And my sample size was 50. Okay, so let's find these probabilities now. Directly from the table. What is probability the selected student is male? Well, let's see, how many males are there total, regardless of whether they have tattoo or not. So that column total, male, it's going to be 20, right? There are 20 males out of 50 possible. So 2/5. The probability is 2/5. Again, you can convert it to decimal or percent. It doesn't matter as long as we get the number. So there's a 40% probability the selected student is going to be male. What is probability the person would be female? If I get it directly from the table, of course, there's 30 females out of 50. That would be 60% or 0.60. Or we can actually use the law of complement. Probability of female is 1 minus probability of male, because there's only 2 levels. I can do that, and that's going to be 1 minus 0.4, which yields the same results. The other marginal probability we want is what is the probability the selected student has a tattoo. So that's probability of H having a tattoo. That's going to be, again, 20 have it. We're looking at the row total now relative to the sample size. So again, coincidental, 40%. Probability does not have a tattoo, N, and that's going to be 30 out of 50, and again, that's 60%. So this is how we find marginal probabilities. Now let's move on to joint probabilities. Let's say we want to find the joint probability of the first one, M and H. Now this event is the event that the selected student is male and has tattoo. Male and has tattoo. Well, this is male, has tattoo, and there are 8 males in that sample that qualify. 8 out of 50. That's 16%, I believe. And there you have it. Okay. The other joint probability is going to be probability of female, and again, I'm not using, I don't know why I have T here. Alright, I fixed that flaw. So next we want to find probability that the selected student is female and does not have a tattoo. So again, we look at female group, those who do not have tattoos. There's 18 of them. 18 out of possible 50, and that's going to be 36% probability. So note how we're defining our own events and finding their probabilities. That's what we like to do in chapter 4, so far anyway. And finally, let's do probability of female or has tattoo. Okay, so probability the person is female or the selected person has a tattoo. Now, if I get this directly from the table, probability of female, well, let's see, we have 30 females. And those who have tattoos, there's 20 of them, right? So far I counted for 50 students. Now remember, the sample size was 50, so far that's the whole class, isn't it? Now, as you can see, the intersection of these 12 females were selected twice, once as being female and a second time as having a tattoo. So that is our duplicate. We need to remove the duplicates, right? So the number of outcomes favorable is 20 plus 30, subtract 12, right? And that's going to make this 38. So that's how many students qualify for that event once we remove the layer of duplicates. So I'm just going to go 38 out of 50, and the way we got this number again was females 30 plus 20 had tattoo, and then we subtracted 12, those students that qualified as having both attributes, and that total again gave me 38 out of 50. So this one is a high probability event. I believe that would be 76%. Okay. Now you could also use for probability of F union H, we can go probability of F plus probability of H minus probability of F and H, and we can also get it that way. Probability of female, well, we found it from earlier, that was 60%. Probability of having a tattoo was 40%. Now, female and having tattoo, well, let's see, 36% were female and didn't have tattoo, so that means 64% are females and have tattoo, right? Or we can go F and N. Let me clear this up. F and N is going to be like this: females and has tattoo. It's going to be 12 out of 50. Sorry, good thing I looked. It's going to be 24%. Okay, and that's going to be 76%. Female and have tattoo. Okay. All right. And there you go. That's the answer to this exercise. Now we're gonna that's probably good enough for this section, as long as you get some exposure to this. We will use an example near the end where I combine all of these into what we've learned so far into one example. But this is the kind of work we want to do with contingency tables. We like to find marginal probabilities, and we would like to find joint probabilities in a contingency table. And with that, we are done with this video.